Hello, welcome back. We're going to talk about concentration units, the 4 that you need to know for Chemistry 112. For this video, you'll need your periodic table and your calculator. I'll show this slide again on the very end of this presentation, but basically we've got molarity, mole fraction, percent, and molality. And molarity is going to be used everywhere. Acid bases, buffers, equilibrium, kinetics. So molarity is the most important, okay? Mole fraction, percent, and molality are only used in chapter 11 here when we describe colligative properties, again on lab 3, but it's just going to be in this section here. So molarity, the big one, capital M, big capital, is very important, okay? All right, first example, we want to calculate the molarity of, here's all this information. We've got a certain number of grams of Tylenol in this many milliliters of solution, okay? So, a few steps we want to go through. Step 1, calculate the moles of Tylenol. All right, so take your grams divided by the molar mass. Notice here how the units cancel. Please cancel your units as you're going through things to demonstrate, and understand, oh yeah, things are working the way they're supposed to. All right, so very small amount of moles here. Step 2, we want to convert the 3.5 milliliters to liters. I'll just show it as a dimensional analysis, but divide by 1,000 or move the decimal place over. You don't really need to show your work here, but I just wanted to show it with units so you could see how things are working out there. So a very small quantity of volume there, okay? And now step 3, you want to calculate the molarity. Molarity is given capital M, and it's just a ratio of the moles per liter, okay? So there's our moles, there's our liter, and when you do all of this, we get 0.034. Notice how everything is 2 sig figs here, because our 3.5 milliliters and our 0.025 grams are both to 2 sig figs. And we just type or write capital M there as the units. So that's molarity. All right, example 2. This is mole fraction. Mole fraction is going to be used when we do vapor pressure lowering, okay? We saw mole fraction before when we talked about partial pressure of gases, but we don't need to even remember that for this chapter, okay? So we've got a lot of different things. When aluminum chloride is dissolved into methanol, we have a bunch of different molecules and ions, okay? We have methanol, which is the solvent. We have aluminum ion, which is one of the solutes, and we have chloride ion floating around, which is one of the solutes. So the first thing we need to do is calculate the moles of the methanol. We have the grams, we have the molar mass, so we just do the division there, and we get 9.36 moles of methanol. Hopefully this should be automatic. You've done it so many times, but feel free to write this down and, work through this, try to wrap your mind around it. We do the same thing for aluminum or aluminium ion, okay? So we have 1.8 grams, and we divide by the molar mass, right, to get the moles of that big, huge creature, the AlCl3. And then there's 1 aluminum per AlCl3, so we just multiply by 1 to get the units to work out there, okay? So here we have 0.013 moles of aluminium ion. We do the same thing for chloride. We are, of course, going to have 3 times as many chlorides, so that's why we have 3 in that conversion factor there, okay? And so you get the moles of chloride, okay? I'm going through this quick because grams to moles should be automatic for most students. It's probably the mole fraction part that is weird, okay? So step 4, you want to calculate the total moles in solution, okay? And that's the moles of every single particle. Remember that a solution can be quite complex. You might have sugar molecules and water molecules in sugar water, or in this weird situation, we have a bunch of ions and methanol all in that solution, okay? So you just add them all up, and I get 9.41 on my calculator, okay? So that's the total moles in this total moles of individual particles in this solution. And then the step 5 is to calculate the mole fraction. It looks like an X, and if you want to write X on your lab reports and your homeworks, that's fine. But this is actually the Greek letter chi, okay? Chi is kind of like a curly X there. And so the mole fraction is the moles of chloride divided by the total moles. So it's just a fraction. There are no units. The moles cancel out. If you want to cancel this out with a little highlighter pen of yours, feel free. So that's just the mole fraction there, okay? So a pretty small number, 0.0044, all right? Example 3, mass percent, okay? This shows up a lot at the grocery store when you're talking about bleach, 5.25% sodium hypochlorite, or hydrogen peroxide, it's 3% hydrogen peroxide, something like that, okay? So mass percent is just grams of the part divided by grams of the whole. So we need those parts. So first of all, we calculate the mass of the solution. Remember that the mass of the solution is the solute, that's the aluminum chloride, and the solvent, which is the methanol. So add those up, you get 301.8. All right, you need the total mass. Now, step 2 is to calculate the mass percent. And we're interested in the mass percent of the aluminum chloride. So it's just going to be 1.8 divided by 301.8. And you get 6.0 times 10 to the minus 3. Now, that's in decimal form. You want to convert this to a percent. The way you do that is you move the decimal place over two places, and then you write a percent as kind of the units. And then I like to write the chemical formula too so that we know what we're talking about. We could write the percent methanol or the percent of a different component in there, but we're just interested in aluminum chloride, okay? So there's your formula. It's pretty easy to do. You just need to find the total weight, and then you just get the fraction, and be sure to express it as a percent. I've noticed some students don't know how to convert decimals to percents very well. All right. Example 4 is molality. Molality is critical when you talk about freezing point depression and boiling point elevation, okay? And we're going to do this in Lab 3 and a lot of problems in Chapter 11, okay, in the OpenStax textbook. So here we've got salt water, okay? We've got 3.8 grams of salt. We've got 250 milliliters of deionized water. We mix it up, and we want to know what is the molality of that solution, okay? So it's a strange unit here, okay? So MOL stands for moles, right? So we want to calculate moles of NaCl. We take the grams, we divide by the molar mass. I went ahead and just did this on my periodic table. You've got 1 sodium and 1 chlorine, and that adds up to 58.44. All right, and I get that many moles of sodium chloride. Step 2, you want to calculate the kilograms of solvent. Now we're given 250 milliliters. A good study tip to have in your flashcards, if you're keeping them, is to write down the density of water is equal to exactly 1, right? It's 1 gram per milliliter, all right? So 250 milliliters is equivalent to 0.250 kilograms. Step 3, you want to calculate small m. That's what we use to abbreviate molality. Please be very careful when you're abbreviating molarity, which is capital M, and molality, which is small m, and moles, which is MOL. And we don't have an abbreviation for molecules, thankfully. Okay? So this is just moles divided by kilogram. It's that ratio there, similar to molarity. Moles divided by kilograms, that equals 0.26 small m, and then I like to put the chemical substance after it, okay? So that's 0.26 molal sodium chloride, all right? Here are the various equations used to calculate the concentration units we'll see in Chapter 11. You've got molarity, which is used for everything in the class from here on out. Mole fraction is just used in Chapter 11, and mass percent and molality as well, just used in Chapter 11. Thanks for watching. Please like, please subscribe if you are so inclined, and have a great day.